Welcome to class. I think you're all there. I hope so. Talking to the Black Void today. Okay, we'll do it that way. So today we're gonna continue on. It would be really nice if some of you could put your cameras on if you're in some place nice. Thank you. Um, it's just nice to know that there's people listening to me. So we're gonna continue working with Laplace transforms today. And you've got one more homework assignment due on Monday after Thanksgiving break. So just keep that in mind. And you've got a reading assignment, another one on Wednesday. So I am kind of in the process of going through your exams. Your multiple choice grades are up, so you can review that and let me know if you have any comments on those. The exams are going to take me a little bit longer to grade, so I'll probably finish them up over the next weekend. I'll just let you guys know that for anyone that might be concerned about your grade, there is a late deadline to withdraw or to change. You can still change to the P plus P F grading policy. So the difference is you can't do this online yourself, but now there's a one-page form that you and I would have to sign to approve that. But I'm happy to approve any of those. I think the deadline for those is like the last day of classes, actually. So you can decide up until Friday of the last week of classes. Okay. So any questions about that before we get started? I'll also say that your FCQs, which are the student feedback for faculty, basically, you should have gotten an email about that today. Those are available, so please do fill out your evaluations for all of your courses. That feedback is really important for our department. It goes into making decisions about promotions and all of these things. So we definitely care about your comments about the class. And more importantly, it helps me improve things for the next group of students. Okay, so we were talking about the properties last time. So I'm on worksheet 21 right now. There were a couple of things we didn't finish up on that one, and then we'll spend most of the class today working on the next worksheet. And so at the very end of this worksheet and pretty much all the others on Laplace transforms, there are a table of these common Laplace transforms as well as properties. So this is something that you guys will be given during the exam. So you're allowed to use this stuff during the exam. And the property that we haven't gotten to yet was this last one. So we did end things last time talking about how we can calculate the Laplace transform of derivatives, and that was part of your assignment. And so the last one is if we know how to take the Laplace transform of f, then we can figure out how to calculate the Laplace transform of t to some power times f of t. And here the assumption is that n is a natural number. So these are things like 1 and 2 and 3, not fractions or negative values. So the proof of this, I'll just put the outline over here. So definitely not expected to prove this. We need results that we don't know. There's something called Leibniz rule that we would need to use to apply to prove this. But if you're curious about how the proof goes, I just kind of sketched the outline below. But for those that have taken or are taking Math 3000 and have been practicing your proof techniques, this is a great example of where proof by induction is really useful technique for proving this result. So basically what this is saying is multiplying by t to the nth power inside the Laplace transform is equivalent to taking the nth derivative of the Laplace transform. And we have some sign change that we need to keep in mind. So rather than kind of go through the messier one, I thought it might be nice just to get an idea of how that induction process works with like a concrete example as opposed to the most general thing. So let's consider, we want to take the Laplace transform, and this is on the table, but let's kind of just verify where that formula comes from on the table. So let's say we want to calculate the Laplace transform of t to the nth power times e to the at. And what's good to know here is that we already know how to do the Laplace transform for an exponential. So let's just first think about what would happen if n were 1. So if n were equal to 1, right, then we'd want to calculate the Laplace transform of t times a of t. And we certainly could try and go through the definition, but we'll use the properties and formulas to do this instead. So the property says that if we're multiplying by t, then that means we're going to take the nth derivative of the Laplace transform of f. In our case, f is e to the at. So the property says we're going to multiply by -1 raised to the power of n, and then take the derivative of the original Laplace transform. And depending on the power of t, that's how many derivatives we would need to take. And so all I did over here was just take the derivative of 1 over s minus a. So you could use the quotient rule or the chain rule on that one. And we would get, keep in mind that when I take the derivative of this, I get a negative sign that comes up top, but then that becomes positive when I multiply by the leading negative over here. Any questions? And then if we move down for f of 2, just to see how this induction process might work, now we want to calculate the Laplace transform of t squared times e to the at. And so this we can think of as taking t times the Laplace transform of t e to the at. And how, if you've never seen mathematical induction before, then the idea is, we can use the previous case to show that the next case would work. So over here, we could apply this property again, where now we're going to consider this entire thing, right, as the function that we're multiplying t by. And so then this property says what we can do is take -1 to the power of n. And so here we're, again, just multiplying by 1 more power of t. So we're going to just multiply by 1 power of -1. And then we're going to take the derivative, the first derivative of the Laplace transform of t times e to the at, which we just obtained in the previous step. And so then we take the derivative of this and we simplify, and we are getting the formula that matches up with what the book says. So the general formula in the book is that if we're taking the Laplace transform of t to the n times e to the at, then the formula looks like n factorial over s minus a to the n plus 1. So over here, we show that formula for the case n equals 1. Our n factorial in this case is 1, and we have s minus a to the n plus 1. Here we would get it for the case where n equals 2, and then we could go on and use induction. So for those that have seen induction, here's how that would look in this step. If you haven't seen induction before, don't worry about it. You won't be asked to prove this. Any questions? Okay, so if you're thinking like, how might we be expected to use this property on a homework or an exam question, as I said, I wouldn't ask you to prove it or do anything with induction, but it might just look like this. So we know what the Laplace transform of the sine of bt, in this case, the sine of 2t. So let's use that and this property to figure out what would happen if I took the Laplace transform of t squared times f of t. And so what we've got over here,
Could you go back up after this?
yeah. And so here what we're going to do is use property L5 to calculate this thing over here. And so what I circled in blue is what property 5 would be for n equals 2. So we multiply by -1 to the power of n, and then we take the nth derivative of the Laplace transform of f. So in this case, our f of t is the sine of 2t, and we know from the table that the Laplace transform of the sine of 2t is 2 over s squared plus 2 squared. Okay, for s bigger than 0. And this you can read off from the table. You've just got a b value of 2. And so if I want to use this property, then what I need to do is calculate the second derivative of the Laplace transform of the sine of 2t. So in this case, we would get that the Laplace transform of t squared times the sine of 2t would be -1 squared, since that would correspond to n. Times the second derivative of that. And so I don't want to get kind of bogged down in the calculus there, but we could use the quotient rule and calculate a couple derivatives of that. So that's how you could apply this property to calculate Laplace transforms of some additional functions. So I will scroll back up in a sec, but any questions about this? So there was a question about this, maybe?
Yeah, I just needed to see the rest of it. Sorry.
Yeah, I'll post, to be honest, it's not that important to prove this thing inductively. What's more important is to apply it in a case like this. So these notes are all posted. So if you've got a question, I'm happy to answer it now. If you're kind of curious to read through this more carefully, these will be up online, so you can check these out too. Okay, so you've got a homework problem that's going to ask you to use some of these properties. So to kind of just summarize things, let me open up the next worksheet. But any last thoughts before I check out the next one? Okay, so we're gonna start heading towards now. We've got all of our tables and we've got all of the properties that we're gonna need to now try and solve some differential equations using Laplace transforms. So again, these are the values that you're given. We kind of just did something very similar to this. We just proved this property. So you'll have these and these properties. And so, you know, properties 1 and 2. Okay, this tells me that the Laplace transform is a linear operator. So we can break up sums and we can pull out constant multiples. Properties 3, 4, and 5, these are a little bit more complicated. But we can think about property L3 as saying, when we multiply a function f of t by e to the at, and then take the Laplace transform, then this is the same thing as taking the Laplace transform of the function f we said that when we multiply by the exponential, that has the effect of shifting the original Laplace transform horizontally. If A is positive, then it's going to go to the right. If A is negative, then it's going to go to the left. And if we wanted to say do the same thing for L5, the one that we just discussed, then we can see that this one is saying, well, when we first multiply f of t by t to the n, this is equivalent to taking the nth derivative of the Laplace transform of the original function f of t. So that kind of tells us that when we multiply by t to the n and then take the Laplace transform, that's equivalent to taking the nth derivative of the original Laplace transform, and there's some sign correction that we might need to apply as well.
For e to the Laplace transform of t to the n EAT, would it be s is greater than 0 or s is greater than a?
So yeah, so this does shift it. So it depends. So if this has a domain of say s is bigger than alpha, then the domain of this shifts the domain as well. So this domain would be s has to be greater than alpha, but we shift that to the right by a units. Yeah, so whatever the domain of the original function was, the new domain is going to be shifted to the right by a units.
So in the example we just did, s would be greater than a.
Which example are you referring to?
Just go up to the table. The EAT to the TN, is that s supposed to be greater than 0 or supposed to be greater than a?
Yes, you're right. Thank you. This is this shifts the transformation. That's right. So this should be s is bigger than a. You're right. Yeah, I did. That looks correct over here. I forgot that one. Yeah. Yeah, so these are basically saying the original domains were 0, so the new domain is 0 plus a. Yeah. Thanks. Okay, any other questions, comments? Okay, so I think just writing out these sentences to explain them definitely helps when you have to apply them. So it's great to see the formula, but it's great to summarize what that formula actually means in more everyday terms. Okay, so let's say we want to solve this second order differential equation over here. So we've seen these. This is like a second order differential equation with constant coefficients, non-homogeneous because we have a forcing function over here. So we certainly could find the characteristic equation, find the general solution, find the particular solution, and then plug in these initial conditions and get the solution to the initial value problem. So we could So that certainly is a way to solve this. And we've seen that those can take a little bit of time, specifically if we have some initial conditions that we then need to go back and worry about. So we can solve this differential equation using Laplace transforms. And let's kind of see what happens when we do that. So my kind of first step here is going to be, I've got some differential equation, and we're going to take the Laplace transform of both sides of that differential equation. So if we're given that this is equal to that, then applying the Laplace transform to two things that are supposed to be equal should result in two things that are equal. So then we can use these properties of Laplace transforms. So first is by properties L1 and L2, which are the linear properties, we've got that this can be broken up and then we can split up the sum and differences and pull out constant multiples. Okay, and then by property L4, and so when you're showing your work, it's going to be really useful for someone who's reading it and grading it and trying to follow it to actually state what properties you're using. So property L4, this was the derivative property. And so I'm going to use that to write out what the Laplace transform of y double prime is. And I'm going to let kind of capital Y of S denote the Laplace transform of lowercase y. So we don't know what y is. Y is the solution, so we certainly don't know what the Laplace transform of y is. So we'll just leave it as some unknown thing for now. Okay, so this property L4, if we apply it to a second derivative, would tell us that it's going to be s squared times the Laplace transform of y, which is capital Y of S. And this is kind of the typical notation that people use. Sorry, I have a hard time differentiating, not in the math sense, in the normal sense, a lowercase y from a capital Y. So I'm trying to make those very, very obvious. Okay, so what I just applied there was property L4, which says if I'm taking the Laplace transform of the second derivative of y, it's going to equal s squared times the Laplace transform of y minus s of y0 minus y prime of 0. Okay, and both of those bits of information are given to us. So one point to make here is this only works Laplace transforms if we're trying to solve a second order differential equation with initial conditions. If we don't have initial conditions, then we don't know what to plug in for these values, and this method can't be used. So just keep that in mind.
Professor, could you repeat that?
Yeah, so this property of what do we do when we take the Laplace transform of derivatives of functions depends on knowing the value of y at 0 and the derivative of y at 0 and so on. So we can only apply this method if we know what those values are, and that means we can only use this method if we have initial conditions. So
L4 only if you
given
have
these
initial
conditions, I'm covering this up with my thumb on my iPad, like you could see it. But if we were just given that, we couldn't use this method because what would I plug in for the values for this and this, we wouldn't know. But as long as we do know those conditions, then we know exactly what to plug in for those values of y0 and y prime of 0. So yeah, so let me just do that. So over here, we would have s squared capital Y of s, and then y of 0 is 0. So that term goes away, right? We have 0 times s, and we've got that y prime of 0 is 1. That comes from plugging in value 0 and 1 in those places there. Okay, then the next term in the left side of this differential equation was the Laplace transform of lowercase y. And again, we're just using capital Y to hold the place for that. We don't know what that is. Okay. Then for the Laplace transform of t, we can just use the table unless we're told we're not allowed to, but you're allowed to. We can use the table to just identify that the Laplace transform of t would be 1 factorial over s squared. So we get 1 over s squared. And we had this leading negative sign over here that comes out over there. So step 1 is very intensive with properties of the Laplace transform. And let me just say, like, one advantage here, we have like a slightly more narrow set of problems that we can solve because we need initial conditions. But we no longer need constant coefficients in front of here. I just did this because I didn't want to start with like an extremely complicated example. But if I had t's or t squared or e to the 8t's, then we have properties to handle those as well. So now we actually can extend this to a broader set of differential equations where the constants no longer have to be constant. So we can deal with non-autonomous differential equations in that sense. Okay, any questions about that step in the process? It takes practice, certainly getting used to these properties and these shortcuts. So it's almost like relearning a different type of integration in some sense. Okay, step 2 is totally algebraic. So now what we want to do is solve for y of s. And I left off my s here. So this means we're going to group all of our YS's together on the same side. So I've got 2 of them. I want this one and this one. So you've got s squared times y of s. And then we're going to move everything else to the other side. So that means we're going to add that 1 to the other side. And now we've got everything that has the capital Y together, all the terms that don't have a capital Y on the other side. And then we can factor out Y from each of those terms on the left side. And I'm just going to add the 2 terms on the right side, put them over a common denominator. So this tells me that the Laplace transform of y is 1 over s squared, right? If I divide both sides by s squared minus 1. So for this one, right, we're not doing anything really with Laplace transforms at all. This is just all algebra at this stage. Right, and our solution for the differential equation shouldn't be the Laplace transform of y. It shouldn't be something that depends on s's. It should be y of t, right? It should be some function y of t. So the last step is to now do the inverse of that operation. So if I want to solve for y of t, it's inside this Laplace operator. What we're going to want to do is try and identify what function y of t, when we take its Laplace transform, is 1 over s squared. And I'll flip back down, but we can come over to this table and then try and identify, right? We had like 1 over s squared. So before we were kind of looking down this column and then identifying the Laplace transform. Now we're going to do the inverse. We're going to look down this column and then try and identify what function has that Laplace transform. So I would look down this column and say, well, what seems to be close to 1 over s squared? Well, it looks like this one over here, right? This is the only one that has like an s to a raised to a power on the bottom without adding some other term to it. So I can see that this looks like that for a value of n, not 2, excuse me, n is equal to 1. So this tells me the inverse Laplace transform should just be t to the first power. So we're just inverting that process. So now we're going from the Laplace transform to the original function. So it's almost like the anti-Laplace transform here, like an anti-derivative. Any questions? Okay. Okay, and that just gave us the solution to that initial value problem that we started with. So as far as like whether it's any better than doing the process that we had before, find homogeneous particular, find the undetermined coefficients, etc., I think really depends on the problem. So I'm not saying what we did earlier was totally pointless. We have different ways of solving this, and one might be preferred over another depending on the problem. Okay, any questions? So, you know, this part of the process, finding the Laplace transforms using the properties, we focused on that aspect of it up to now. Okay, step 2 in part B, there's nothing new other than some algebraic techniques there. But I do want to think about this stage over here, right? We had a particularly easy one here to recognize. We wanted to find what function has a Laplace transform 1 over s squared. The more complicated this expression is, the harder it's going to be to identify what had that Laplace transform. I want to focus on that step of the problem because that's the hardest part of it. So this process is what's called finding the inverse Laplace transform. And we just use the same typical notation of -1 to denote inverse operator. This is not reciprocal, so just keep that in mind. So the way that I would use that notation to write out what we just did would be to say, when we write this over here, it's exactly asking that function, right? What function has Laplace transform 1 over s squared? And we just simplify that question. That's what we do in mathematics with notation, is it just gives us a more concise way of writing that out. Okay, questions? Okay, so let's get some practice with inverse Laplace transforms. So your reading quiz for Wednesday is not going to be something new. It's going to be, let's make sure that we practice this part of the process so that on Wednesday, this is more familiar with you and we can just really focus on the differential equations. So your reading quiz is going to be very, very similar to these types of questions in question 3. And let me pull the table of integrals over. That's going to be useful to have. Let's see. Sorry, I'll be right back. All right. So definitely when you're doing this exam, I would highly encourage you, that table and those properties should be clearly open someplace easy for you to refer to, and that's totally fine. Again, that's not anything illicit that you're doing on the exam if you do that. So really the game here is look at this thing over here and then try and identify what form it looks closest to over here, right? Identify what the values of B or A, what some of these parameters might be to figure out what the inverse Laplace transform is. So we're no longer going from lowercase f to capital S. We're now going from capital S to lowercase f. So this one over here, we just did this one by saying it looks like this with an n value of 1. So it might help if you don't see it initially to try and take the original thing and rewrite it in a way that it very clearly matches one of these things over here. And from this, we can see n is 1. So its Laplace transform f of t would just be, in this case, t to the first power. And we don't need to worry about the domain of the original function. It's only the Laplace transform that's going to have some domain issues because we want to make sure that that improper integral converges. We don't have to worry about that when we do the inverse Laplace transform. So I would say, you know, when you're doing these, kind of the first stage is to identify what type of function does it seem we have, and then identify what the parameters might be, the A's and the B's and the N's and so on. So I just want to get a sense of what everybody is thinking. I'm going to open up a poll. And so these are the options. So this is now in regards to part B. So if I want to calculate the inverse Laplace transform of this, the question is, which of these rows of the table do you think we're going to be in? So if you think it should be an exponential function, then you would guess that. If you think it's a power function, you would guess this. If it looks like that, then you're telling me that I think it's a sine. If it looks like this, then you would say, I think that is the cosine. So that's kind of the first stage, is to figure out, well, what type of function am I dealing with? And then fiddle around with, well, what would the values be for either n or a or b? Okay, take another 10 seconds, please, to get your answers in. Okay, so that was unanimous that we had a sine of bt. And so, yeah, when you see things like something squared plus something else squared, that usually rings the trig bell, right? This should be a sine or a cosine. And then it really depends on the numerator, whether we have a sine or a cosine. So for the sine function, notice right, we have a b up there, whereas meaning a constant, whereas for the cosine, we have an s up there. And so in this case, right, we have a constant up there, so that's why we're going to get the sine in this case. And what's the value for b that we would have here? 2, yes, thank you. And this is something to be really careful about, and that you don't just want to pick off that value. It might help to first write that as that is what squared, and the thing that you're squaring is the b. Oh, sorry, I forgot to share the results. In case you're curious, there it was. Questions? Okay, gonna relaunch this. And let's think about now question C. Which of these types of functions do you think we would use for this one over here? Okay, take another 10 seconds, please. Okay, thank you, everyone. So again, we have a unanimous decision. We don't need to go to a recount here. This seems pretty compelling evidence that cosine of B of t seems like the reasonable choice. And then, so let's think what that would look like. So what do you think the value of B is going to be in this case?
3.
3. That's right. So here, because we have s squared plus 3 squared. So that's right. So here we've got B is equal to 3. And so seems like f of t equals sine, or excuse me, cosine we have here. Seems like a good candidate. But if we actually take the Laplace transform of this, sorry, then we would get s on the top over s squared plus 3 squared. So we don't get back what we started with, right? We started with this. So how do you think we can fix our guess so that we get 4s on the top instead of just an s on the top?
Multiply by a constant 4.
Yeah, and so here we have this nice property that constants can be moved in and out of Laplace transforms. They can be therefore moved in and out of inverse Laplace transforms as well. That's right. So we can fix that issue by saying, well, we could move a 4 in there. It would just come out, and that gives us the right constant on top. Okay, any questions? Okay, we'll try,
Silly professor,
yeah.
would you have to declare that if we were trying to answer this? Would you have to put like L1?
No, you don't need to say which property you're using there. I would say when you're given a problem that says like using the table and the properties, find the Laplace transform of so-and-so, then in those problems, yes, it would be good to say like by this property we get this. Yeah, not with the inverses here. That's okay. Okay, so last one, let's take a look at D. And what type of function do you think this one would be? All right, take another 10 seconds, please. Oh, that's not what I wanted to do. Okay, 3 unanimous polls. Good. We're on our roll today. So good. I think this part seems to be going well. So yes, this one would be an exponential since this one right, kind of looks like this up here. Okay, meaning we don't have any s raised to a power in the denominator. So that's a good indication that we've got an exponential. And so over here, what's our value in this case for a? I'm going to say this is going to look like e to the at with a equal to
-6.
-6. That's right. So we say, okay, f of t equals e to the -6t. Won't quite work because that Laplace transform would have a 1 on top. So how do we fix that?
Multiply by constant 2.
Yep. So we just fix that by putting a 2 in there. So this would be the inverse Laplace transform for that. So this sort of process is going to be really important for that last step in the solving differential equation using Laplace transform. Any questions about these examples? Okay. If not, then we need to think about more complicated ones because the things that we're going to get out of these differential equations typically are not going to be this easy to find the inverse of. So it might involve doing a little bit of algebra to rearrange the expression first so that it more clearly looks like something in the Laplace transform table. So kind of one thing to notice from the Laplace transform table is that we get lots of things with s squareds on the bottom when we have sines and cosines of some sorts. We haven't done any that look like this, where we have e to the at times the sine or cosine of b of t. So yeah, some of yours on the homework will be kind of, the ones that you have on the reading assignment are going to be more of, you should be able to just look at that, look at the table and be able to line it up. But I want to do some that are a little bit more complicated. So you won't have to do this on the reading quiz, but you'll definitely have to do some of these on homework. So initially, this does not look like anything that was in that table. But if we could rewrite the denominator, well, yeah, I already did that, like this, then it more clearly is going to look like an e to the at times a sine or times a cosine. Let me see if I can plot this over here. So this stuff over here kind of looks like the denominators for these over here. So kind of our goal is to say, okay, if I can rewrite this denominator in this form, which is in other words saying we want to complete the square really on this thing, then it's going to be more clearly in a form that we could probably pair it up. Because I have an s up here, it seems plausible that I might expect to get some sort of e to the at cosine bt as my inverse Laplace transform. We just have some work to do in order to recognize that this function can be written in this form. So the idea here is we want to take this denominator And maybe just for the sake of not using the same letter B that we have over there, I'll just call that a K. And so what do you think should go in there? If we're going to get s squared plus 4s plus 11.
-2.
That's right. We'll have a -2. So we have a negative times a negative. So over here, right, we can just plug in 4 over 2. That's where the 2 comes from there. And then we need to add some constant onto this so that it matches up what we started with. So if I have s squared plus 2 squared, this gives me s squared plus 4s. So the linear term and the quadratic term match up, but the constant term does not. So we've got 4 over here. We would like to have 11 over there. So how much additional stuff do we need to add for this to match up?
7.
7. Okay, and this is going to be something common that you're going to need to do on a lot of these problems. So I tried to pick things that commonly come up when we're doing this to focus on those. So if you're thinking about, well, like, how could I do this? Well, the process was we first kind of matched up the quadratic and the linear terms by saying inside here should just go this constant divided by 2. And then we just figured out that this doesn't give me back the 11. So K is going to be whatever correction I need to match up the constant term. So now we've got S of S is equal to S plus 2 over S plus 2 squared plus 7. Right, and that looks very, very close to the very last entry in the table. Where we've got A is -2 and B, right? Again, you want to be careful, is not 7, but the square root of 7. Oh, I think, yeah, oops.
If that b squared, the plus 7, is a negative, how could we represent b? Because it's squared, so it will never be negative, and it's plus
Yeah,
7.
if you have a negative term, if you have a negative sign over here, that's right. It's not going to be one of these over here. So it's possible that it might be something like this, because this has s minus something raised to a power. But you're right. If you had a negative sign here, then this process wouldn't work for that. So problem 4 was a case where the term in the denominator, this quadratic term, it did not factor cleanly over the real numbers. So that's why we went ahead and did this process. So let me just say, if the denominator can't be factored, then this is a useful process to go through. The next example, we actually have a denominator here, and this can be factored. So let's see what happens if we do that. So this problem is different than the previous one that we did, particularly because this one we can factor the denominator. And looking at our table, I don't think this is that helpful off the bat. Any thoughts on what we might be able to do for this one?
And just split up the function and see if it matches anything that we're used to.
What'd you say, sorry?
Just go ahead and split it up. Have 5s minus 10 over s minus 4, and then do the same with the s plus 2 to see if it matches anything that we recognize.
So I do want to think about how we might be able to break this up, but not sure if I'm understanding the suggestion, but we don't want to do this.
Is it the partial fraction decomposition?
Yeah, that's right. Our old friend, partial fraction decomposition. Good suggestion to try and avoid doing that, but we can't. And the reason why is we're going to take the inverse Laplace transform, and I can't break up products, but I can break up sums with Laplace transforms. So if I can take this quotient, or this, which is a sort of a product, and write it as a sum of things that I can do the inverse Laplace transform of, then that's going to give us a strategy here. So if we can factor it, okay, then we've got to come back to partial fraction decomposition. So this is going to come up in a number of these problems. So how that works is we would take sorry, I don't need this. I don't know why I started with B. So we can write that as sum of two fractions, and then we would want to, set up equations to figure out what A and B would need to be. I don't want to do that algebra, if you'll allow me kind of bypass that, but that process, you should find out that A is 2 and B is 3. Just to give some indication about where that solution comes from is we would just add these together, and then we would get an equation that says, well, AS plus BS, that should give me 5S. And looking at the constant terms, we get A minus 4B, that should give me minus 10. So we just match up the terms that we get here with the original terms in the numerator. And then solving this system of equations, that's where the 2 and the 3 come from. So now this Laplace transform taking the inverse Laplace transform. Since we've proven that this function f can be written as this sum, then we're just saying this sum we can break up. And then we can pull constants out just like we can with Laplace transforms. And then we've got things now that are pretty easily identifiable from the table. Right, that would give me this one over here is e to the 4t, and this one over here is e to the minus 1t. So that's where those come from.
Is the bounds of S important with these?
It's not. We actually don't even know what it is over here, but when we're given a lowercase f and we're finding the Laplace transform of that, we need to be careful because when we evaluate the resulting improper integral, it might not converge. So it only converges for certain value of s's. So we kind of need to put that stipulation on it. But when we go in the reverse direction, we don't have any domain issues that we need to worry about with the function f. Okay, so we will pick up with doing, there's a couple more that we can start off with on Wednesday. You'll have some practice for some of them on the reading assignment as well. I want to make sure that we're good with these. And then for the rest of the semester, we're going to be basically looking at different types of differential equations that we can solve with this method. So on Wednesday, we'll be focusing mostly on how now we can apply all of this to solve some differential equations. So as far as the homework goes, yeah, I think the last problem has a couple of solve this differential equation. So maybe we're not quite there yet, but you should be able to get going on the rest of the problems up to that last one. Okay, so I'll stop here. We've got some additional time, but if you have some questions, you're welcome to stick around. But I don't think we're going to be able to do this last one in the remaining time. So rather than rush through it, we'll just start with this one on Wednesday. All right. Well, thanks everybody. Have a nice afternoon.